So that's the first, the second column with, okay, log frequency. You actually hear the real part and the imaginary parts of g of I omega. This will be needed for the second type of plotting we're going to be doing later on, the Nyquist plots. And then the next column is log AR. And the last column is the phase lag in degrees. So we want to do what? A body plot. Click body plot. And here is the plot, and I didn't go high enough in frequency. Okay, let's go back and redraw it with maximum frequency higher. Click go back, and you have among the choices change mean max frequency, so we don't have to re-enter the transfer function. So click that, put the same point 0, 0, 1 as minimum, put 10 as maximum. And 1600 points. So I'm redoing it with 10 maximum. New data, polygon. That's much better. Maybe I should do it also with 100, but let's look at this a little. Okay. So you have two plots. Orange. I should have used orange for the AR on the board anyway. Orange, log AR, the left line. You see what we just discussed. What is log? K was 100, right? What's log of 100?
10.
2.
2. Yeah, 10 squared. Okay.
So look at the orange line, orange white, the left axis is for the orange line, which is log AR. You see the straight line asymptote at 2, at log of K. And here is the straight line with slope minus 1. Where do the two intersect? What's 1 over tau here? 0.1. What's log of 0.1? Negative 1. Negative 1. You see, that's where the corner is if I were to take, if you take straight line this, and straight line this, the two would intersect about here. You can see minus 1 is right here. Do you see that? Everybody says how the log AR plot is exactly what I drew on paper there. Now the delay is really small. You see here the sum, the brown is the phase lag, and you see instead of 0, you have minus 0.57, that's practically 0. So you can see, if I didn't have the delay at all, it would be ending at minus 90. The delay is what's making it go down exponentially. To see fully the exponential, let's change the maximum frequency from 10 to 100. Let's go back. Change min max frequency. Let's put the same point 0, 0, 1 as minimum, 100 as maximum. Always 1600 points for the plot. Okay, you can see it very nicely now. You can see it very nicely now what I was trying to draw there. The tan, the minus tan inverse of omega tau would have just leveled off at minus 90, about here. But we are adding the exponential decay of the delay, which makes it now go exponentially towards minus infinity. Wait a minute. Doing okay?
What did you change to get that?
I changed the maximum frequency to 100. I went back, changed the maximum frequency to 100. You don't have to be doing it, guys, although it's good practice for you to know how to use the software. But you can just pay attention. Does it make sense? Do you see what I was drawing on paper?
Can you repeat one more time what you said?
Yeah, you can see this is the sum of two pictures. If my delay was not there, then I would be going to minus omega tau. As a matter of fact, if I change this, I'll tell you what, let's repeat the same plot, changing the delay to 0. Then you will see it level off at minus 9. If I had no delay, it would level off at minus 9. The delay adds, going from 0, okay, remember that's the action that applies here, going exponentially to minus infinity. Adding that, while the delay at small frequencies, the delay contribution is practically 0, so pretty much it does what it would have done without the delay. But as the omega gets bigger and bigger, the delay becomes more important, and as omega goes to infinity, this will go on to minus infinity. But we can go back. Let's play with it. If we put delay 0, now it's okay. You can have a problem with the software if you're tempted in just changing something and drawing it again. Most times you get away with it, but many times you won't. The good thing to do is to change transfer function and redo everything. But I'll roll the dice, just change the delay. We'll see if I'm like it or not. So I change the time to 0. Not specific frequency. 0.001 minimum, 100 maximum as I had before. 1600 points. Let's see. Body plot. Okay, here we go. Where is it? You can see now the minus tan inverse of omega tau. It levels off at minus 9. Okay? So when the delay added, the delay was, I wish I brought my umbrella.
Grab the flag. Mike.
Anyone has the razor pointer? No.
Grab the stool.
Nobody takes a picture. Okay?
Oh shit, let me get the camera. wait.
All right. The delay would have been 0 and then exponentially going down. That would be added to this. So you can see, with small delay, we would be staying 0, 0, 0, so the sum would be the same as the Brown curve, but eventually the delay starts going down, and that's what we saw before. Let me go back and change it. At least I won't get up now, right? I don't see anybody sleeping now. Huh? Oh, okay. If same picture, yeah, it might be a small difference calculation, it might be different CPU a little bit. So if we go back to the point 0, 1 I had before, right? Point 0, 1 is the delay I had original. Yeah, okay. So if I go back to point 0, 1 and draw it again, point 0, 0, 1, 100. I'm repeating the previous plot now that you can really see it.
What were you showing us with the stool?
What the delay would have been, the delay would have been 0 and then coming down. So while it's staying 0, the sum of the two is this Brown curve. You saw without the delay, this Brown curve levels off at minus 9. The delay is the addition of the exponential decrease. Now, if the delay becomes much bigger, the minus 90, that minus times omega tau is going to get better. So let's go back and increase the delay from 0.01. Let's make it 0.1. Quite that one. Okay. So here I increase the delay to 0.1. I'm still using 0.001 and 100 as the scale. 1600 points always. So now you see what is happening. You can see that the delay hit faster, and you can see now the delay dominating very soon. At the beginning, you still see the part that goes towards minus 90. Now, if I decrease the delay to 1, then you'll almost see just exponential decay. If I make it 10, for sure you see just exponential decay.
Let's make it 100.
No, so let's change the delay to 1. So if I make it 1,
Damn. Weird. Should totally make it 100.
okay? Now you can even, now it looks almost, because minus 90 is squished at the very top, right? So you don't even see the minus tan inverse. You can see the exponential, that is the delay. Okay? One note, if I have the frequency too high, the maximum frequency, and that happens also in every piece of software that has frequency response, it's impossible to do that. You start seeing on the phase lag things like that. That happens because how do you calculate the inverse of the angle? I have logic in there that, remember, tan inverse is periodic, the tan is a periodic function. So if it drops up to 360 degrees, the logic can capture it. But if among successive points it drops more than 360 degrees, the logic can't catch up with it. Even the professional software is that way, so I don't feel bad about that at all. And you will see an artifact like that. So if I take the same plot and I still make maximum 100, make it maximum 1000, change minimum maximum, you start seeing this happens. So I'll make again 0.001, maximum instead of 100, 1000, 1600 points. I believe we'll see the artifact, otherwise I have to go higher. Yeah, okay, you see this artifact. Okay, that's not real. In reality, we have continued motion. It happens when the maximum frequency is too high. Okay, so be aware. Okay, so we understand how to use the software for body plots, right? Okay, let's return now back to understanding something a little bit more about body plots. And luckily for you, that's the only body plot we calculated by hand, the first order plus time delay. But I mentioned that this business started before there was computer, before computers were available, were widely available. And why do we have log AR on one side and linear scale on phase lag? Why is it log on the amplitude ratio side and no log on the phase lag side? It all comes down to how body plots were constructed in the old days. We saw equation star 1. Whenever you had a transfer function you wanted to plot, you would break it into pieces and you would know what it is. First order without time delay, you would know what's the time delay, you would know what's for the PI part, and so on. And so you would be able to draw individual ones. But look at that. If I had a linear scale here, and I had the plots of individual ones, if I didn't have a log scale, this would have been a product. You can do product geometrically. But log of GZ, the GZ is the product, sorry, magnitude of GZ is the product of magnitude GZ1 minus GZ2. If I change to a log scale, what's the log of the magnitude of GZ? It's log of product, and what's log of product? Sum of individual parts. That's sum of log of magnitude of GZ1 plus log of magnitude GZ2. So if I have log scale on the AR side, and I plot for individual transfer functions what the body plot is, I can add the curves very much like I was doing for the delay with tan inverse and the delay, sorry, for the phase plot by adding the tan inverse and the minus omega. So in the old days, let's say you had to do a body plot of, let's say you had a G you wanted that was, let's say, 4s plus 1 over 10s plus 1, 5s plus 1 e to the minus 7. You would define it as G1 equals 4s plus 1, G2 equals 1 over 10s plus 1, G3 equals 1 over 5s plus 1, and G4 equals e to the minus 7s. You would do the individual plots. Here is one, here is another, here maybe is another.
Wait, what are you showing us? What are we doing? I lost you.
So, in the old days, how would you do a body plot of something like that?
Should I be copying this down?
It's an explanation, up to you if you're copying it down. I'm explaining to you why the y-axis is log scale on amplitude ratio and it's linear on phase length. So now you can do everything with computer, and I could have done it if I didn't want log scale. I could have done it whatever scale I want. I have the table of the data, I can plot them any way I want, right? But in the old days, they were able to draw the asymptotes. And you saw how close it hugged the asymptotes. So as an approximation, they were drawing the asymptotes, and then they were adding up the asymptotes. So let's say I had this. This would be broken down as the product of 4 transfer functions. G1 would be the numerical polynomial, G2 would be 1 over 10s plus 1, G3 1 over 5s plus 1, G4 the delay, and it can be a lot more complicated. And then each one of these you would draw the asymptote. So this would be the asymptote of G1, this would be the asymptote, let's say, 1 over 10 here. That would be G2, this would be G3, G4 would be just simply at 0. Remember that has amplitude ratio 1, log of 1 is 0, so that would be adding 0. So the delay is adding 0 to the amplitude ratio part, because the magnitude of the delay part is 1. So log of 1 is 0, so we're adding 0 for the delay. And they would add up all those lines to get the log AR of G. On phase lag, it's additive without the log. Equation star 2. The magnitude, sorry, the phase lag is the sum of the phase lags of individual components of the problem. So for phase lag, the same addition was happening with just adding without the logs. So if you have, I don't know if they still do the addition, but certainly I know the Stephanopoulos textbook is doing additions and so on. Unfortunately, I've messed up one at least. So you don't need to do that. Obviously, we're doing everything by software. I'm not going to ask you to do any of that. I just want you to understand, okay? So you understand why the AR plot, the AR part of the plot is log scale, because individual pieces are additive in log scale. The argument part, though, the phase lag, is normal scale, because normal scale is additive. Felix.
I don't understand, how do you add the lines?
Well, okay, this number is 0, and this number is 1, and this number is 2.2, and this number here is 7. 7 plus 2.2 plus 1 is 10.2. So the